in order to do some later material in the course, we need to take a sidestep and cover section 4.7 because a lot of times it isn't covered in Calculus 1. Now, before we do that, we want to just kind of make a quick note of all of these properties of limits and such that we're supposed to know from Calculus 1. I mean, most of these are pretty straightforward. That's why they're not on a formula sheet. For example, the limit as x approaches c of the function x is c. Kind of obvious that you can add limits, you can subtract limits, multiply and divide them, provided, of course, that the denominator is not equal to 0. Take the powers, take the fractional powers, right? You can do roots and things like that. And it all works out. I mean, the only thing with roots is you have to be careful that if m is even, in other words, you're taking something like a square root or a fourth root or a sixth root, then you have to have a positive function value. Otherwise, you're in the imaginary and or complex number system, and it's beyond the scope of our course. Let's put it that way. Also, we learned that if you have a polynomial, because polynomials are really easy, then the limit as x approaches c of that polynomial is that polynomial value of c, right? So there's nothing really to worry about. And a rational function, which of course we all know is a polynomial divided by a polynomial, right? That's what a rational function is. So if you take a polynomial divided by a polynomial, then the limit function or the limit value of that function will be equal to the function value at that value, as long as the denominator down here is not equal to 0, right? Because you cannot have denominator equal to 0, right? Well, at least that's what you learn in Calc 1. And here we're going to learn there's a ways around it. All right, so section 4.7 is about L'Hopital's rule. L'Hopital being the French mathematician that thought of it. And it's all about limits, this particular section, so it'll be a little bit of a throwback. Now, when we were young, naive Calculus 1 students, we want to know what really happens when you divide by 0. And the answer is, well, several things. It could go to infinity, it could go to negative infinity, it could go nowhere in particular. You basically have an unknown value. But also there's things like 0 divided by 0 or infinity divided by infinity. And we have kind of competing rules in our lives about this. First of all, we learned that division by 0 generally makes some kind of infinity. But we have 0 divided by 0, right? 0, anything over itself is 1, right? Wrong. Not with 0 over 0. And then 0 divided by anything is 0. So we have no real rule for how this. Is it 0? Is it 1? Is it infinity? And the answer is it could be any one of those things. It could also be 4. No, I'm not kidding. It could be 4. So it could be any number at all. And infinity by infinity, same thing. So those are called indeterminate forms. I'll highlight them for you. So 0 by 0, 0 divided by 0, which is this, and infinity divided by infinity, which is this, are indeterminate forms. They're the base indeterminate forms that we work with. All right, so let's look at some problems that we should have done in Calc 1. This should be review, so hopefully this will work out beautifully for you. All right, so if I'm going to take the limit as x goes to 1 of x squared minus 1 over x minus 1, you'll notice that if I just substitute 1 in right away, right, I'd have 1 squared minus 1 over 1 minus 1. So it'd be 1 minus 1 over 1 minus 1, which is 0 over 0. That's indeterminate. Okay, well in Calculus 1, the way we fixed that was algebra. So we say, all right, well I'll take the limit as x goes to 1. Yes, you still have to write that. And then I will use all of my algebra tools in my arsenal, which I have x minus 1, x plus 1. I know how to factor. And since I factored, then x minus 1 divide away and just leave me the limit as x goes to 1 of x plus 1. You still write the limit x goes to 1 until you actually get to do substitution. So we tried substitution off the bat and it didn't work. It gave us an indeterminate form. So then we have to use algebra. Right? That's what we're doing. And then you say, okay, well, that's wonderful. That's 1 plus 1, which I remember first grade is 2. Or is that kindergarten? Anyway. All right. And you can see it on the graph here. And I, of course, have that graph in Desmos for us to look at. It's right here. So you can see that on this function, as we approach 1, it's approaching that value, right, of, whoop, there, it was right there. It says undefined. See it? There is no actual function value there because it's 0 over 0. But I can tell the limit is 1. As I approach from the left and the right, from both sides, the y value is approaching 1, even though, or excuse me, approaching 2, even though the function value itself does not exist there. And of course, because this is a function, right, you're approaching y equals 2. That's your function value. You don't actually get there because you cannot actually substitute 1 into the original function as given. And this function, x plus 1, is not the same. It's equivalent, but it's not the same. So they're not equals. Even though we put an equal sign over them, or with them, they're not actually equal. They're equal except for that 1 point, except for 1, 2. All right, what about this little guy right here? So we're going to approach infinity. Well, you can't put infinity in. I mean, for one thing, you get infinity over infinity. That's indeterminate, right? So we don't know what infinity over infinity is. Is it 1? Is it 3? Is it, 0? What is it? And the answer is it could be anything. Indeterminate means it could be anything. Right? Could be a number, could be infinity, could be negative infinity, could be all sorts of things, right? Any particular number you like. All right, so what could I do? What could I do? Well, I could multiply by 1 over x. So I could take the numerator, and I could take the denominator and multiply by 1 over x. And if you're thinking, hey, that looks familiar. Yes, because that's the trick that we've been using in this chapter. We're using algebra. We're multiplying by 1 over 1. Same thing we're using for doing integration, because of course they're related. So it's the limit as x goes to infinity of, all right, 2x divided by x would be 2, plus 1 times 1 over x is 1 over x. X times 1 over x is 1, plus a 1 over x. Now I know you're thinking, well, how in the world did that help me? Well, remember, we know that the limit as n goes to infinity, I can just put a little recall, of any constant over n is 0, where k is a constant. We learned that, right? If you take any number and divide it by infinity, everybody gets nothing, right? So what is that going to mean for us? Well, this is going to mean that when I put infinity over here, it's going to be 2 plus 1 over infinity, and then 1 plus 1 over infinity. And 1 over infinity, both of those are zeros, right? So this is 0, this is 0. And that means that we have 2 over 1, which is 2, which you can see right here on this graph. That function is approaching y equals 2. And of course I have it. So let's look at it. All right, so here's our function, which is the blue curve. And you can see that as I move to the right, as I let x get larger and larger and larger, I'll just kind of swing this over here. If you look at those y values, 1.89, 1.87, 1.89, 1.8, 1.901, it's getting closer and closer and closer to 2, because 2 is our horizontal asymptote. We actually learned that in Calculus 1, right? So this is y equals 2 is the horizontal asymptote. And we actually learned that's how you find those with calculus in Calc 1. All right, so there were a couple algebra tricks we used for Calculus 1. Then there was one other trick we used in Calculus 1 that I want to review, which is finding the limit numerically, right? So this is more recall from Calculus 1. So we had some recall from Calculus 1 originally. Oops, sorry, in this example, I forgot to highlight that. Sorry. And then we have now more of it. And that is we can find limits numerically. You can find them with a table, essentially. Now notice if I put in 0, if I try to substitute, look what's going to happen. I'll get e to the 3 times 0 minus 1 over 0, which is e to the 0 minus 1 over 0, which is 1 minus 1 over 0, which is 0 over 0, which is indeterminate. I mean, we've already learned that that could be 2, that could be 5, that could be whatever. So we don't know what that is. All right, so what we can do is we can use a table. And of course, Desmos will help us do this right here. So I named my function right here. And this is something we haven't really done much in Calc 2. We've mentioned it. So I said, here's my f of x right here. And then I put in a table. A table is an option amongst the 5 major options that are currently available in Desmos. And so I put in a table and it says it's x1. So then I call this f of x1. I have to name it that way. And then I put in these values that are the values from the table. And you can see, right, negative 0.1, that's actually where the table starts down here. Negative 0.1 goes to 2.59, negative 0.01 is 2.955, and so on. All right, so I'm going to copy those values over onto the notes. I'm going to pause, and I'll be right back. You can do the same. Pause me and write all those numbers down. And interestingly enough, these tables don't work like tables that you're used to in algebra. That can get people into a little bit of trouble. What you're doing is you're starting off large away from 0. So starting with the large values of x, like 0.1 and negative 0.1, which don't seem that large, but they are in terms of limit context. And we work our way in closer and closer to 0. 0.001 is a lot closer to 0 than 0.1 is, right? 100 times closer, or right? Because this is the tenths. Oh, actually, yeah, it's 100 times. 10 times 100 makes 1,000, right? So you work your way in. Don't be fooled by algebra tables. So algebra tables, you've always learned to, go up by the same amount every time and that kind of thing. That's not how these are going to work. So these are small values here, and these are large values out here. Right? If you missed that in Calc 1. All right, so now we're going to make a speculation. What do we think the limit is? Well, I don't know about you, but I think it's 3, right? So our speculation, the limit as x approaches 0 of that function is 3, right? It seems an awful lot like it's going to be 3. We're getting very close to 3 on both sides. This is a little bit above, this is a little bit below over here. So now we're going to verify it graphically. And of course, I have the graph pre-drawn for you, which is very kind of me, but it will not always be pre-drawn. Now I want to shift this point off for a second. So when you look at the graph, when you just put this function into Desmos, I should have mentioned this in the previous one, it doesn't make a hole, right? It's not going to be there automatically. But if I let my cursor kind of swing up, right there, see it? When x is 0, y is undefined, see? And so what I did was I put in this point just to make sure that that was clear in the graph. So I added a point and made it an open hole like this. I just chose a different style. I chose the open circle one, right? So that's how I made that function look like that. And you'll notice it is approaching 3, right? As I approach from the left and as I approach from the right, I'm sort of with my cursor doing the same thing I'm doing with the table. I can see where those y values are going to, and they're going to 3. So sure enough, it does verify because the y value for that puncture, that hole, I have to put into the graph myself. But sure enough, the y value of the puncture, right? We learned that those are point discontinuities in Calc 1. Sometimes they're called holes. It just depends on what your instructor called them, is at 3. So the limit as x goes to 0 of f of x, I don't feel like writing the function out, is 3 is verified. Graphically, I should say. Right? So the graph verifies what we thought with the table. Now, why did we not use an analytical method? Because there's no easy algebra tricks available to us. It's not as straightforward as some of the other functions that we worked with to simplify that value. F of x equals e to the 3x minus 1 over x. We don't have an easy way to do that. All right, so what if it's an ugly function and we don't want to use numerical values? If only there was another way we could do it that would be analytical, that would count as analytical, but we could use it with indeterminate forms. Huh? That's what L'Hopital's rule will be. That's what the rest of this section is about. So L'Hopital's rule will do that for us. L'Hopital's rule will be our analytical method, and we'll be able to use it even when it's indeterminate and ugly. L'Hopital's rule will work out for us.